This is lecture 11B for Calculus 2. It's on sequences. It is on using algebraic rearrangement and absolute convergence to determine the convergence of sequences. For some sequences, if you algebraically rearrange the term, then the limit is easy to find. I'm not talking about rearranging the order of the terms. I'm just talking about rearranging the terms themselves. And one of the goals, or the goal, is to isolate a sequence of known behavior. For example, if you can isolate 1 over n, you know that as n goes to infinity, 1 over n goes to 0. Here's an example. And if you notice in the homework that I tried to set you up for the different methods to use to determine the convergence of the sequences in the homework. But in this example, we have the sequence 3 plus 6n squared divided by n plus n squared. And we want to, of course, take the limit and see if the sequence converges. So what we can do here, and this is very common in this sort of situation, is to divide numerator and denominator by n squared. So when I do that, I get this rearrangement. 3 over n squared plus 6 divided by 1 over n plus 1. Right. We like this form because in it you see the p sequence for p equal 2. It's 1 over n squared, and you also see the harmonic sequence 1 over n. You know that the limit of both of those is 0. So let's take the limit of the sequence as a whole. And using the rules for taking limits, we end up with 6 as a limit for this sequence. Here's the first new theorem for testing convergences of sequences, and this is to look at the absolute value of the terms of the sequence. And the theorem says that if the absolute value of the terms of the sequence converge to 0, and 0 is in caps for a very good reason, it has to converge to 0. If it converges to 10, the theorem doesn't hold, or the result of the theorem doesn't hold. Okay, so if the terms of the absolute value of the terms converges to 0, then the limit of the sequence itself is 0. Here's an example. I have the sequence minus 1 to the n over n. These terms look like minus 1 plus a half minus a third plus a fourth minus a fifth, and so on. I can take the absolute value of the terms, and that would be 1, 1 half, 1 third, 1 fourth, 1 fifth. In other words, the absolute value of the terms is just the harmonic sequence. I know that this sequence converges to 0, therefore the original sequence also converges to 0. And the operative word here is 0. Just to give you a little better understanding of this theorem, because first it might seem sort of like, where did this come from? Look at this theorem as though it's an extension of the squeeze theorem. If I have terms that alternate, if I take, let's say I take the absolute value of the terms, all right, then the absolute value, I can use the absolute value as the maximum. It should be an equal sign right here. Let's say the absolute value is equal to c. Let me correct that right here. If I take the absolute value as equal to the term that's greater than our original sequence, because I'm talking about here is, let me find the pen. Here's the pen. Okay, so what I have here is that b to the n is always less than or equal to the absolute value. Bn is minus 1, it's always less than 1, right? Okay, so that gives me the upper bounding sequence for my squeeze there. Now, okay, b to the n is always greater than or equal to minus b to the n, or rather, minus the absolute value. Okay, right down here. So I'll have to put minus the absolute value of b to the n is always less than or equal to the original sequence b to the n. Right? That gives me the function on the other side of the squeeze theorem. Now, see, this is why it has to converge to 0. Because if this converges to 0, if c to the n converges to 0, then minus c to the n also converges to 0, and that squeezes b to the n also to 0. If c to the n converges to 10, then minus c to the n converges to minus 10, and b to the n, of course, we don't even know the behavior of b to the n in that case. That is why we need to have it converge to 0. So if we're going to, let's apply this to that example before. We have, here is our sequence. We'll call it b to the n equals minus 1 to the n over n. Its absolute value is 1 over n, so the original sequence is less than or equal to 1 over n, because that's its absolute value. It's greater than or equal to negative of this absolute value, that's minus 1 over n. Both of them go to 0. That grabs the middle sequence, the original sequence, and also converges it, and it will also converge to 0. So by the squeeze theorem, the original sequence converges to 0. You don't have to go through the squeeze theorem. You can use the idea of absolute convergence itself. Use that theorem. If the absolute value of the terms of the sequence converge to 0, then the original sequence also converges to 0.